Last time, let's summarize what we have learned last time. So besides what we've done about the graphing the graph of the function, let's talk about the concepts that we talked about last time. So first of all, limits. So we are talking about multivariable function, so I will denote my multivariable function as the following. So this function has m coordinate as a value, and it takes r coordinates as an input and m coordinates as output. For each of output coordinates is a function on n coordinates and has a real value. So this is going to be our common notation. Note that I had a vector sign here, just to mention that this f is not a real valued function, but a vector valued function. Okay. So what's the limit of this kind of function? So when we write that as a x vector approaches to a, and I'm taking a value of vector value function f, and let's say this is going to be my vector value. So this is a notation saying that the value of function f approaches to value of v when vector x approaches to vector a. Okay? But when you have to show that this happens, you have to be rigorous about how to prove that the limit is actually equals to this vector. And the method of proof is using the epsilon delta method. Probably you heard in the single variable function, single variable calculus, or not. But I'm not going to talk about that because it's a purely mathematical argument. But let me emphasize again that this approach of x to a is not only along the straight line, but it means that in any direction or in any path, the limit of function must be equals to v. So by all kinds of paths, we should check that the limit is equals to some value. So in other words, if you want to show that the limit does not exist, then you can find two different paths whose limit of value of function f is different. Okay? And let's talk about the differentiability. Well, let's talk about the continuity. So continuity here. It's a simple because I can just take the limit as a value of function. If this equality happens, then we say the function is continuous at a. Okay? And intuitive argument about continuity is that suppose that we have x, y, z space, and this is our graph of function. Then let's say we have a here in xy plane, and we probably have a point in the surface of the graph. And if x approaches to a, then the trajectory on the surface of graph should approach to value of function as z. So this function has a single valued function, single real valued function. So we can just identify value as the value on the z-axis. So if you have a hole on this point A, or if you have a sharp edge, well, not sharp edge, or like a diverging point on A, then you can say this is not continuous. And let's talk about the differentiability. So it's a little bit different concept than continuity or limit, but it uses the notation of limit. So our definition last time was we are taking a denominator as the norm of x minus a vector. And on the numerator side, we have fx minus fa minus what? Some matrix M times x minus a. And also, I want to point out that this M is M by n matrix. And this vector, which is n-dimensional vector, is considered to be n by 1 matrix. So when we take a multiplication of two matrices, we get n cancels out in the middle. We get m by 1 matrix. So we take this m by 1 matrix as m-dimensional vector. So in that case, we can subtract the value of function with the value of m-dimensional vector. So in the numerator, we have m-dimensional vector. In the denominator, we only have a real value. So we're just taking 1 over the norm times the m-dimensional vector. So the result of limit should be 0 vector, m-dimensional 0 vector, in order to say that function is differentiable at value a. Okay? So let me say it again. I'm not going to write that as a sentence. Listen carefully what I'm saying here. We say that function f is differentiable at a if there exists some matrix, m by n matrix, such that the limit of these things equals to 0 vector. That's the definition of differentiability. So we had a question, what is m in this case? So there was a theorem saying that if all partial differentials of f, so when we say partial differentials of f, we say that the partial differentials of these coordinate functions f1 to fm are continuous at a, then what's inside of m is simple partial differentials. So the layout of the elements of this matrix is the following. So first of all, you take the first coordinate function f1 and take the partial differential by x1 and then xn. And when you change row, you change the coordinate function until you get fm xn. So basically you get m by n matrix. So just remember that this is a theorem. So theorem assumes that your partial differentials are continuous. In that case, it says that the function f given by this coordinate function f1 to fm is differentiable, and the differential written as m is given by the matrix of entries whose entries are these partial differentials evaluated at the point A. All right. So this is, I think, what we have. And then we have discussed the meaning of differential. So this is called a differential. At A, and we discussed the meaning of differentials. So when we say the differential, we're not going to write m as a usual symbol. We're going to write it as d, a, f, or sometimes people put f prime, the same notation as single-valued function, but remember that this is a multivariable function. So there are several different notations for differentials. Well, let's take easy one. Let's take an easy notation of differential. What's the meaning of differential? So first of all, this differential is a matrix, okay? So when you talk about the differential of single-valued function, this is a number, but single number is considered as 1-by-1 matrix. So you can also think about the differential of single-valued function as a matrix too. So when you have a matrix, you can multiply some vector on the right. So since this matrix is m by n matrix, when you multiply a vector on the right, the vector has to the dimension of vector has to be n. And when you think about n-dimensional vector, you have to recall that this function, the domain of function is also n-dimensional. So suppose I draw this as a two-dimensional, but think about this as a n-dimensional space, domain space, and this as a target space, which is m-dimensional. Suppose that I'm having a curve inside this n-dimensional space. And let's say at some point, let's say A, my curve is moving at certain direction. Okay. So for now, let's not think about direction of movement. Let's think about the trajectory of this curve. So I'm going to translate each point on this trajectory to the target space by the function f. Because at each point, I have an input variables. So when I plug in that input into the function, I get m-dimensional output, m-dimensional vector as an output. So I can draw the trajectory, the output of the trajectory as, let's say, like following. So since I'm drawing not a graph of function, it's just the trajectory, I can draw like this function, these figures. So let's say I call this trajectory as C, and so C is just a collection of n-dimensional points, and this is the results of this trajectory by evaluate by function f. And there is a point which corresponds to this point A. Suppose that it's here. Okay. So now let's think about the vector again. So when I pass through the point A, suppose that I'm moving along this direction. So it's a tangent direction to this curve. So if I move slowly along this trajectory line and think about just when I pass the point A, on the target space, it will pass through the point FA. And since I'm moving on the domain space, the corresponding point on the target space is also moving. And when it just passed the FA, it should have a velocity, the instant velocity at that point. Suppose that my instant velocity is about this direction. It should be tangent to the output curve here. So this is what the function f does to the domain space and the target space. What happens? What does this differential does? So let's name this vector v, and let's name this vector w. So differential maps differential at A maps a tangent vector v to the tangent vector in the domain space. So let me write that as an equation here. F prime A times v is equals to W. So you have to remember what the meaning of v and W are. So v is the tangent vector to some trajectory line, and W is the tangent vector to the trajectory line corresponding to the trajectory line in the domain space. So basically, you can change the configuration of your trajectory curve. Suppose that you can think about your curve is not like this, but let's say like this. Again, let's say this is C prime. Then your tangent vector will change to this direction. And of course, since you change the trajectory curve, the output trajectory should also change. But what is not changed is the point that the trajectory line passes at the point A. So at that point, the instant velocity vector should change, but I will denote it as same W. So no matter what kind of trajectory line you choose, the velocity vector at the point A is mapped to the velocity vector of the output trajectory line. And the relation is given by differential F prime. It makes sense because this is m-dimensional matrix. So this is m by n matrix. And we take this vector v as n-dimensional vector. So we can take it as an n by 1 matrix. And W is a tangent vector inside of m-dimensional space. So it has m-dimensional space, m different direction, right? So it's an m-dimensional vector. So it should be m by 1 matrix. So when you multiply m by n matrix with n by 1 matrix, you get m by 1 matrix. So this is the exact meaning of differential. Okay. So application is simple, but let me just give an easy example, just make-up example. Let's say I have a function fxy goes to x plus y and x minus y. So if you understand what this function does, you can map the domain and target, and you can imagine how this function f transformed xy plane to UV plane. So let's say this coordinate, first coordinate as u and second coordinate as v. So think about the grid line and the domain space. Let's say we have these grid lines, the horizontal ones, which means that I'm changing x coordinates but fixing the y coordinates. For example, when I take y equals to 0 line, what happens to the target space? What kind of trajectory it corresponds to the line y equals to 0 in the target space? V equals u, right? Because y is 0, so x comma x equals to uv, so uv are equal. So this is the line corresponding to y equals to 0. Let me just put it as the same notation here. When I change to y equals to 1, what happens? So uv follows the equation of x plus what? Right, if you calculate in your head u is equals to v equals to u plus, I don't know, u equals to v plus 2. But let's think about just naively plug in this number. When you plug in y equals to 1 in the equation of u and v, u is equals to x plus 1, and v is equals to x minus 1. So if you have a parametric equation like x plus 1, x minus 1, you can imagine that the direction is parallel to 1, 1 vector, and it passes through the point 1, minus 1 when x is 0. So you can imagine that here is 1, minus 1, where this trajectory parametric equation passes through, and the line is parallel to 1, 1 vector, which is also parallel to y equals to x, u equals to v. So this is the line. And you see that when you move up your y values, you can easily guess that this line is going down here, and y less than 0, then it goes up. So these are, the yellow lines are the target lines, corresponds to these horizontal lines in the domain space. What happens when I take the vertical lines in the domain space? Like this. So let's suppose that I take the x equals to 0. What happens to what's the corresponding line in the target space? Tangent lines are minus 1 slope lines, right? Yes. So we do the same thing with the previous part. So we have x equals to 0, so we have u equals to y and v equals to minus y. Note that x, y are independent variables, okay? So you can take x or y as the parametric values. So y changes from minus infinity to plus infinity, so you can imagine that this y comma minus y is a line which is slope minus 1 and passes through 0, 0. So we have like this here. And how about when x equals to 1? So it parameterizes to 1 plus y, 1 minus y. So the slope is the same, but it passes through 1, 1. So 1, 1 is here. You can guess that our line x equals to 1 corresponds to these lines, and so on, up or down. So you see this function kind of rotates and a little bit dilates these lines in between. And it kind of transforms this xy plane into some different shape, right? Let's think about vectors. So suppose that I'm at 1, 1 in the domain space, and I'm moving along the x direction by 1, 1, 0 in the unit direction. Okay? So 1, 1 corresponds to 2, 0 in the target space. So it should be start from here somewhere. 2, 1. Does it pass through 2, 1? Maybe. Yeah, let's say this is 2, 1. Okay. So when I move my 1, 1 point along the x-axis, parallel to x-axis, to in the unit speed, in the direction of 1, 0, in which direction does 2, 0 in the target space moves? Direction of slope 1. the speed is, you mean it moves along this direction, but how fast does it move? With square root of 2. So it should be 1 comma 1. The instant velocity is 1 comma 1. That's what you mean, right? Why do you think so?
Because the y value doesn't change in the xy coordinates. So only the changing coordinate is x value. And we already experienced that if the x value changes, then its slope will be 1 in the u-way coordinates.
That's how you found out the slope, right? So since when we fixed y and move x, we know that this line corresponds to this slanted line with the slope 1. So we know that the direction of movement is 1 comma 1. But how did you figure out the speed of this movement?
Because I just used the given coordinates of at x comma y. If the x increases with value 1, each component will increase as a scalar value 1. So it is 1 comma 1. For velocity is 1 comma 1.
Right. So when x increased by 1 in the unit of time, for example, then this u and v coordinate also increased by 1 in the unit of time. So we know that this must be velocity of 1 comma 1. So that's how you find out by knowing how this function looks like, how this function changes the domain space to the target space. We can make it as a little bit more algebraic. So for example, I'm taking a trajectory ct inside of the domain space starting from 1 comma 1 with the unit speed of time. So when time t increased by 0 to infinity, it moves along 1 comma 1 to 1 comma 0 direction with the speed of 1 comma 0. So I'm going to take this trajectory inside of the function f and then see what's going to be on our target space. So let's take a composition of these two functions. So I'm taking, so let me write this as a 1 plus t, comma 1. So this is my x and this is my y. So plug in there. We have 1 plus t, comma 1 is equals to 2 plus t, comma t, right? So we have a parametric equation which is two-dimensional, which lies inside of target space. So let me call this as a d, t. So what you're looking at is, this is our ct, and this is our dt. Okay. Now, when you measure the speed, instantaneous speed, or instantaneous velocity, what you have to do is take a derivative, right? So when you take a derivative of ct, you get the instantaneous velocity of the movement of the point at 1 comma 1 when you plug in t equals to 0. So c prime 0 is the tangent space, tangent velocity of the trajectory line, which is already a straight line. So we get 1 comma 0 here. And what happens to d prime 0? One? 1, comma 1. Right? So it's the same result that you guessed before. So this is another algebraic way to find out the corresponding vector. And now let's apply what we have discussed in the previous part, the meaning of the differential. Let's use the meaning of differential. So we know the formula of the function. Let's take the differential at 1, comma 1. So I'm going to plug in 1, comma 1 after I take all the partial derivatives. So let's name the partial derivative. So what's inside of the first row, first column? What's going in here? It's the derivative of u or v, u, with the variable
X and Y.
in the first column, x, right? So it's a ux, it's 1. And about the second column? U, but 4y, so it's also 1. How about third and fourth here? Vx is 1, and here we have Vy, which is minus 1. So luckily, we don't have any variable in xy. That's because I choose this function as linear functions. But you might have x and y appears. Then you have to plug in 1, comma 1. So anyway, this is equals to 1, 1, 1 minus 1. So that's a derivative at 1, comma 1. So we can only talk about the tangent vector starting at the 1, comma 1 direction, or 1, comma 1 position, and how much it moves in the target domain. So let's think about the multiplication of this derivative with 1, comma 0 direction. So then I have 1, 1, 1 minus 1, 1, 0. And remember how you take the multiplication between two matrices. First of all, you take the row column, okay? First matrix, the left side matrix, you take the row, and the right side of matrix, you take the column, okay? 1, 1, 1, 0, and then multiply each coordinate and then add them all. So you get 1. And the second row, first column, you get 1. Same 1, comma 1, two-dimensional vector. So we had a simple example because we let this point move along the x-axis, parallel to x-axis. We could have moved this 1, comma 1 point to any direction, arbitrary direction, like square root of 2, comma 1. Then if you try to argue the way you did in the previous part, and previously, it's going to be messy. You have a lot of computation. But if you use the derivative, it gets really simple. You simply take the derivative of a function at the point 1, comma 1, which is 1, 1, 1 minus 1. And then multiply with any direction that you want to consider in the domain space. And the result is plus 1 and square root of 2 minus 1. Is the two-dimensional vector, which gives you the movement of the point in the target space along the corresponding trajectory. Okay? Any question? No? Why do I emphasize the meaning of differentials? Because if you understand the meaning of differentials, it's really easy to understand the meaning of chain rule. So I'm going to talk about the chain rule, but chain rule is simple name, but what I really want to talk about is the differential of composition of functions. So we always start with the thing about the single value function. So we had a theorem you probably learned in high school that if you have two single valued functions and you composite together and the differential of the composite function is multiple of two differentials of functions. Let me write that out. So if you have a function f and g, which is single value single value, no, let me say single variable function. Single variable. And let's not go deep into the domain of f is inside of the range of f or something like that. Let's just take a composition and let's call it h. Okay. So h is a totally different function. I want to take a differential of f. Fh. And you probably learned that this is equals to the differential of outside function f. But you have to plug in the value of g, and then you multiply with the differential of inside function. So it's the same thing when you really try to compute the differential, not the derivative. So the derivative of h at a is equals to the derivative of outside function times the derivative of inside function. Right? That's how you learn in high school. Let's talk about the meaning of the differential of composite function in the multivariable case. So let's say my function f is multivariable function on whose output is m coordinate, and let's say I take g as g1, gn as n coordinate function, and let's say this g function is taking L values as an input and spits n outputs, so as an n-dimensional vectors. So here's the picture. So we have L-dimensional space is mapped by G onto n-dimensional space. So each coordinate function gi takes L-dimensional vector as an input. And then we're going to take a composition, again, taking this function fi. So each of fi takes n-dimensional vector as an input and spits a each fi is a real values function. We have a collection of m coordinate functions, so overall it's m-dimensional, but each of fi is a real values function. So here's our situation. Let's pick a point A in the domain of the function g. I want to make this point move onto some direction, let's say v. Okay. In order to think about this movement, you can imagine a trajectory whose velocity vector is v at the point when it passes through the point A, or you can simply take your trajectory as a straight line parallel to v with the parameterization same as the similar one that I did here, a times t times v. Whichever trajectory you use, you have to make the point move to the direction of v when it passes through A. Now, let's think about what happens to the target space of G. At the target space, this curve will change to another curve, but there is a point when it passes through A, it also passes through the target trajectory, GA. Okay? So there we have also some vector when it passes through the corresponding point. Now, let's take another trajectory as if this was our original trajectory and then see what happens in the target space of F. Then we also have another trajectory, and let's give a name for GA, let's say B. So suppose that I have FB at here, and we again have an instant velocity vector, u, right here. Although, what did we say about the relation between v and w? Since it's connected by the function g, what was the relation? How do you compute your velocity in the target space? Times A times V, right. How about relation between W and U? Times W, right? Now let's combine these together. So let's multiply this f prime b on the left and right. You get f prime b times g prime a times v. And that equals to f prime b times w, and that equals to u. Right? So let's think about leftmost term and rightmost term. So in between, I don't care about what happens in between, because I only care about the composition of these two functions, f of g. So for example, I have x here, so I'm taking this function as h function. So x is L-dimensional vector, and I put that into the function g, and g gives us n-dimensional vector, and that n-dimensional vector is put into the function f, and then f gives m-dimensional vectors. So basically, it takes the n-dimensional, L-dimensional vector, and then takes the m-dimensional vector as output. So this is RL to Rm. So if you think about h function, which is given by composition, the h itself doesn't care about what happens in between in the n-dimensional space. I only want to talk about the domain and target of function h. So just looking at the left side and right side here, v lies inside of L-dimensional space. U lies inside the m-dimensional space. This tangent function, a tangent vector, is mapped to this tangent function, a tangent vector at point A. So when you move your point A inside of L-dimensional space to the direction of V, it will move along the direction of U inside of m-dimensional space, right? What kind of thing, what kind of map does that kind of mapping? So we have a movement in the domain space, and it maps to, it corresponds to some movement vector inside of target space. What kind of map does that correspondence between these two vectors. That's the differentials. Differential connects the two tangent vectors in domain space to the target space, right? But we already know that the tangent vector in the domain space is connected to the corresponds to the tangent vector in the domain target space by taking multiplication of these things, right? So in principle, what we want to find is H prime A, the differential, which gives the role of corresponding the tangent vector inside of R and L dimensional space to the tangent vector in M dimensional space. That's what this differential of H does. But you see in the equation above, this F prime times G prime already does that. So these two must be equal, right? This F prime times G prime already corresponds the tangent vector in the domain space to the target space, right? That's what H prime should do. That should be equal thing. Think about the matrix. What's the dimension of this matrix, F prime? How many rows and how many columns? M by? Just F prime. Just F prime. M by N. How about G prime? N by L. And you multiply these two matrices, you get rid of N, and result is M by L. So what about the differential of H? What dimension does this H prime should have? Equally M by L. So dimension-wise, these are two same matrices. And the role of these two matrices are the same. So it should be the same matrix, right? So H prime A is equals to F prime B G prime A. So, well, the B is intermediate term that we have defined just to make simpler. So let's rewrite that here as G A. Okay. So you see, let's compare the derivative of composite function for single variable case and the multivariable case. In the single variable case, you had an outside function, a differential outside function times the differential of inside function. What about the multivariable case? The derivative of composite function h is equals to derivative of outside function times the inside function. But the object that we are taking multiplication is different. Here we have just the real numbers, right? Here we have matrices. But these two matrices are multiplicable because it has the same number of rows and columns. And then, the idea is the same thing. The chain rule, this is called the chain rule. The name is not important. Just you have to understand what it does to, what it really means. So you have a composition of two functions. If you really want to compute the actual formula of the function, you have to plug in these numbers. But if you only know the differential of these two functions, you can find out the differential of composition at that point. Just taking differentials of each functions and then multiply it together. You can you can consider this as a special case of the multivariable case, considering this value, the real value, as 1 by 1 matrix. Okay. Now, let's think about the example here. So example is just to show you that the chain rule actually works. So I'm going to give you F is the same thing as before, and G, let's name any G here. Let's see what happens. I think it has to be the linear function. So any example that you can come up with linear function of U and V? U plus V. Okay, U minus V. All right, what happens? Let's see what happens when you composite these two type of functions. It's the same formula, but when you composite these two, it will be different. So let's think about H prime. So it's a function of UV because I'm going to take F composite G. So I'm going to plug in U plus V, U plus V, U minus V inside of F. So inside of X is equals to U plus V and Y equals to U minus V. So X plus Y becomes 2U, right? And X minus Y becomes 2V. All right. So let's think about what happens to H prime 1, 1. What's the derivative? Two. And the second column? So this is the first coordinate function, 2u. How did you get 2? By
derivative of 2 times u.
Derivative of 2 times u by u. And in here, you have to take a derivative of 2u by which variable, u or v? V, right? So when you take a derivative of 2u by v, partial derivative, what's the result? 0. How about here? The second row? 0, 2. Okay, so it's a constant. So in principle, you have to plug in 1, 1, but it's the same thing here. 2, 0, 0, 2. And let's see what really happens by plugging the lines here. So F and G are sending R2 to R2. So let's say at 1, 1, I am moving in direction of 1, 0. So if I take a parametric line CT equals to 1, 1 plus T 1, 0, at T equals to 0, I'm moving along 1, 0 instantly. Okay. This red trajectory line is mapped to what? Mapped to which line in the target space of G? I think we did in the previous example, right? This is y equals to 1 line, so in the target. So G is the same formula of F that we have drawn before. So in the target space, this red line corresponds to which line? What's the slope of the line corresponds to this red line?
Slope 1.
Slope 1 and passes through 2, 1. 2, what?
2.
It passes through 1, 1. So if you plug in 1, 1 here, 2, 0. Right. So it passes through 2, 0 and has a slope 1, which means it's parallel to 1, 1. Right? It's a simple argument because you can just make x to, in this case, u to increase, but v is fixed, so it passes through 1, it's parallel to 1, 1. So anyway, so when CT passes through 1, 1, it passes through 2, 0 in the target space, and it moves along this 1, 1 direction. Now, let's see what happens to the target space of F, as if this is our original trajectory. So my trajectory, let's say this is dt, is now 2, 0 plus t times 1, 1. So in the target of F, where does it pass when t equals to 0? So you have to plug in 2, 0 in the function f. You have to plug in 2, 0 in here. 2, 0. 2, 2, right? And how about the direction? Parallel to y-axis or x-axis? Y-axis, you mean it moves upward? Why do you think so? Why does it move upward? 네.
그러니까 U랑 V가 똑같이 증가하잖아요. 근데 G에서 U 플러스 V, U 마이너스 V인데 뒤에 U 마이너스 V가 이제 변하지 않으니까 U 플러스 V가 V로만 증가한다.
자, UV가 이 세 개 코디네이트 중에서 어디에 있죠? UV가? 그러니까 UV 코디네이트이 요 세 개 코디네이트 중에서 어디에 있죠? First one. This is U and this is V. What's the coordinate of the middle one? X and Y. 자, 그럼 아까 질문 이제 얘기한 게 뭐였냐면은 여기서 이제 UV가 똑같이 증가하니까 라고 이제 얘기를 했어요. 그렇지만 실제로는 뭐가 똑같이 증가하는 거냐면은 X랑 Y가 똑같이 증가하는 거예요. X랑 Y가 똑같이 증가하면은 여기서 이제 바뀌겠죠, 뭔가가. 얘는 어떻게 돼요? X minus Y. 뭐 제로 제로에서 시작을 했으면은 제로겠죠. 여기서 이제 2,0에서 시작을 했으니까 컨스턴트겠죠. 어쨌든 네. x가 변한 양이랑 y가 변한 양이 똑같으니까 서로 상쇄돼가지고 처음 시작 값이랑 계속 일정할 거예요. 그러니까 이 값이 fixed 돼 있다. How about the first coordinate? Increased by 2, right? Because it add up together. Although it moves along t, t, but here we have 2t. So you can guess that it moves from 2, 2 to the direction of parallel to x-axis by 2, 0. Right? So let's compare the product. Here we have a movement to the 1, 0 direction, and the result was it moves to 2, 0. The speed of, the direction is the same, but the speed is twice much before. But now let's think about this one. Let's compare whether it makes sense to our calculation. So we had 1, 0. So I'm going to multiply 1, 0 here. The result is 2, 0. That's our result. Right? Now, I want to check whether it's same result when I use the chain rule. So chain rule says that my derivative of composite function is given by derivative of outside function times the derivative of inside function. So what's the derivative of outside function f? I think we did the calculation before. So what's in the first row? 1, 1, 1, minus 1. So again, this is not the result because we have to plug in the value of G11. The value of G11 was 2, 0. So we have to compute that as 2, 0. But luckily we have a constant, so we don't have to compute. And what happens to G prime 1? What's the same thing, right? So it's minus 1, 1, 1. So drop all the coordinates here, 1, 1, 1, minus 1 times 1, 1, 1, minus 1. So the result should be 2 by 2 matrix again. What's the entries on first row, first column? 2. First row, second column? 0, 0, 2. Same result, right? So you have to understand why this multiplication gives the derivative. We actually did compute the translation of these vector to this vector using the derivative of g. That's in here. And then we take the derivative of f by translate the vector from here to here. That's the matrix here. So when you multiply 1 by 1, 0 matrix on the right, you're taking a multiplication on the right. So you're taking these matrix multiplication and then these two matrix multiplication. That's the translating the 1, 0 to 1, 1 and then translating to 2, 0. That's all included in this matrix multiplication. But overall, if you really just interested in just the derivative of composite function, you can just simplify as a matrix multiplication, result of matrix multiplication like 2, 0, 0, 2. So that's obtained without plugging the actual formula inside of the functions. Now, why do we even care about the chain rule? So that's our main point. So today I'm not going to talk about the coding, but I'm going to make a scheme of what we are going to do. So let me pose a question. What what does partial derivative mean? So for example, if you have f(x) at a, considering that the function f is two-variable function with the real valued two-variable function, what does it mean? In other words, how would you explain to, say, middle school students the meaning of partial derivative without introducing all these limits over mathematical formulas? How would you intuitively explain the partial derivative? Changing rate of each component of vector. The partial derivative is the changing rate of each component. Is that what you mean? So first of all, I'm taking the value of function as the real number, not a vector. Okay.
Then there's simply just the changing rate.
Changing rate of scalar value in which situation?
Well, with scalar value, z can be maybe wind chill, because wind chill is, the parameter of wind chill is the velocity of wind and temperature of air. So I think that could be the example of that function.
That's very nice. So you're giving a meaning to the value of variable x and y. For example, like say, what does x means in your example?
The velocity of wind.
Velocity of wind, and y?
Temperature of air.
Temperature of air, and z?
Value will be the wind chill.
Wind chill?
Temperature of wind chill, like the temperature that we feel actually.
Oh, okay, wind chill. Okay, that's a very good idea. So we have x as velocity of wind, and y as what was it? Sorry, temperature of air. Okay. And z is the wind. I'm not sure it's right. Wind chill. IL. ILL. Okay, so that's right. Wind chill. So the temperature that people actually feels. Okay, that's a good example. So in that situation, let's elaborate more on these coordinates. So for example, let's say velocity of wind is 10 meters per second. It's quite large, right? So it's like a typhoon, so it's maybe 5. And how about the temperature of air? Let's say 5 Celsius, okay, good one. So 5 Celsius. So what does this mean? Let's say we have a value of partial derivative at 5,5, which means that I'm taking a measurement of partial derivative when the velocity of wind is 5 meters per second and the temperature of air is 5 Celsius degree. Let's say we had a variable -2, let's say. What does it mean? It's an excellent example. I think it's a very nice example.
Tell us that the temperature that we actually feel is -2 Celsius, so it is really freezing.
Maybe. So the answer, what he said is that similar to this situation. So when the velocity of wind is 5 and temperature of air is 5 Celsius degree, that we feel the temperature that we feel is -2 Celsius. That's kind of explaining this equation. The function itself tells you the wind chill, the temperature that you feel, right? I'm talking about what happens when I have a variable. Partial derivative is equals to -2. So I think you already mentioned the rate of change in the first place. So how about you talk about the rate of change in this situation?
Well, it is derivative of x. So it is derivative of velocity of wind. So we have to assume that temperature of air will not going to change. It is constant, and it only tells us how purely the change of velocity affects to the wind chill.
Right, exactly. So how it tells you how the change of velocity affects the wind chill. So now let's take the numbers in. So we are starting at 5,5. What happens when I change? What happens when the velocity of wind changes from 5 to 6? What this -2 could give us? Rate of change, right? So it gives the rate of change of wind chill. So rate of change of temperature that people feels when the velocity of wind changes, but temperature of air remains the same. So it kind of means that when the velocity of wind changes from 5 by 1 meter per second, then the wind chill, the temperature that people actually feels, approximately drops by 2 Celsius degree. It's the same as the rate of change of single variable function, because taking a partial derivative is nothing different but the derivative of single variable functions. When you talk about the meaning of the derivative or differential of single variable function, it gives the rate of change of value of function when you change the x coordinates, right? So our x coordinates in this case is the first coordinate, because we take the x coordinate here. And when it changes to the positive degree, or for example 5 to 6, then approximately the value of function changes by -2. So it's a nice example and nice explanation here. Let's summarize that here, or make a little bit of general argument here. So for example, if we have fxa, then this gives the rate of change of f when the x moves x changes to the direction of A. It's a vague idea, vague expression, but what it means is that I'm taking the coordinate. Oh, I'm sorry. Well, this is not exactly the same. When A changes to the direction of 1, 0. So I'm starting with the point A and changing the first coordinate, which is called x coordinates in this case, by 1, 0, by 1. And it means that I'm changing my A coordinate to 1, 0 direction. And I want to find out how much the value of function changes. So when I change the value of A, very small amount, then the actual change of value of function is very small. But I really want to see is the rate of the change. So this fxa is actual difference of x coordinates approximately with the actual difference between the value of function, right? So when I change my value of x by delta x, I want to see how much the value of function changes. And I want to find out the ratio between these two numbers. That's approximately the partial derivative, meaning a partial derivative. Actually, when you want to compute the partial derivative, you have to take the limit as if you take the definition of derivative of single variable function. You have to take, so x just goes to 0, x and f of x plus a1, a2. Oh, by the way, the a1 and a2 comes from the coordinates of a vector, and minus f a1 and a2. So you're making this delta x smaller and smaller. So I'm taking x instead of delta x, but you can replace it to delta x if you want. Delta x here. And then if you keep doing it until delta x almost goes to 0, then the limit is the partial derivative. What about partial derivative in y? You're doing the same with the y coordinates. So instead of delta x, you're taking delta y, goes to 0, and you're taking the ratio between actual difference of the value of function and the y difference. Right? Now, can you think about some geometric meaning of partial derivative? So any geometric meaning? Maybe because I majored in differential geometry, that I always try to think about geometric things in geometric ways. So I want to think about the meaning of partial derivative in geometry. In the more precisely, how would you interpret the partial derivative inside of a graph of function?
The domain two-dimensional space,
Uh-huh.
and codomain is one-dimensional.
One-dimensional.
Space,
Uh-huh.
or scalar value.
Uh-huh.
Then we can visualize the graph.
Right.
And in that case, the partial derivative means that we actually focus on a plane.
Mm-hmm.
I mean, if we based on the function that the derivative of x means that we fix the y values,
Mm-hmm.
and then we actually imagine the plane that goes through the y value,
Mm-hmm.
but also parallel to z plane.
Right.
Then we can have a graph exactly the same with the single variable function.
Exactly.
Then
Uh-huh.
we can find out the geometric mean.
Right.
It will be the slope.
Uh-huh. So, sorry, I did just, Hyungyu answered perfect. That's how I exactly imagined. I mean, tried to explain, but he answered perfectly. But people who listen from Zoom probably didn't hear. So let me elaborate what Hyungyu said. So let's think about the case when we have two variables and the value function is just a real number. We can draw a graph of function in XYZ space. Let's say this is our graph of function. And suppose that I'm taking value A and try to think about the derivative in x direction. That means I'm taking a plane. You can think about it as a cutter knife, which is plain, just flat plane knife, and you cut your graph in this direction, and you're looking at the intersection of this knife and the graph. And you move your knife and then make it flat here. What you see is the intersection or section of your graph passing through this knife. So this knife is located at A2, which is the coordinate of A that I defined before. And then probably it has a domain here. And here should be A1, right? I'm taking x direction knife, which is also parallel to z-axis. So this graph must be exactly the same graph as if it's a single variable function. So I can take a derivative or take a slope of tangent line. And this slope of tangent line should be the partial derivative in x direction. Right? So it's a slope of the section of the graph with is a plane parallel to xz plane at A. Okay. Now, I have another question. So, partial derivative gives you the rate of change when you move your point to x or y direction. What if you want to move your x and y at the same time? What if you're moving at 1, 1 direction at a certain point? How would you compute the rate of change of that function? The question is how to compute the rate of change of f xy in a general direction u. let's say u is two-dimensional vector. How would you do that?
Add the function of derivative of each component, like f sub x plus f sub y,
Mm-hmm.
and that would be the total change of
Mm-hmm.
z value.
Right. So, so he knows the answer, all the answers. So here is A, and let's say I'm moving along the direction of U. So here's my final point, but I'm not actually move my point A to here. I'm considering that A is moving in this direction in this speed. But suppose that I have a graph here. I can approximate my rate of change as if A is moved along the x-axis by u1 direction, so u1, 1,0, and also in y direction by u2, 0, 1. And on the z, in the z value, I can imagine that the rate of change, the change of z value is sum of change of in this direction plus in this direction. So as if I'm moving along this direction and then also again by this direction. So these two lines are the tangent lines or tangent vectors, you can imagine. It's not lying inside of this, on this graph, which is the surface inside of three-dimensional space. Just the tangent line. But actual difference is different, but I can imagine that this delta z and delta z2 here. So delta z1 is equals to the rate of change in x direction. So when I change my x coordinates, I can imagine my change in z value is proportional to actual change in x direction. So this is approximate change of in z direction when I move my x direction. And how about z2? This is when I move my y coordinates by u2. So when the change is actually u2, I can imagine that my actual change is approximately this much. Okay. So you can imagine that this u1 is approximately delta x and this is equal to delta y. Then everything is same. So this is how you interpret the partial derivative. That's how I exactly just make it into equations. So more precisely, well, this is equal, okay? And then when I move actually from A in the direction of u, I have to add these vectors together. So I can imagine that my approximate change of z value should be sum of these two rate of change. I mean the change. So fxa times u1, fya times u2, right? So let's see. This so if you want to start talking about the rate of change, then you have to introduce the notion of time. So if you divide your value with the time, okay. Now this becomes the first coordinate in the velocity function, considering this as the distance and this is the time. Now it's the velocity in x direction, and this is the velocity in y direction, and the rate of change of z value, the function value, is equals to the chain equals to the partial derivative times the first coordinate, partial derivative times the second coordinate. This is how you can imagine that the rate of change should equal. how about we choose other methods? Since we considered the geometric meaning of the partial derivative, let's try to do similar thing with the direction of u. So when we cut this graph in x or y direction, you get the slope of the section is the meaning of partial derivative, right? How can you obtain the rate of change in u direction with similar procedure like cutting? Any idea, Jian? The simple analogy, if you cut along x-axis, you get the slope, which is the partial derivative in x. If you want to get the rate of change in u direction, you have to cut in which direction? Mm-hmm.
Just cut the three-dimensional shaped surface to the u direction.
U direction, right. So u direction. Let's take the cut in u direction. So here is our graph, and here is our point, and here is, it seems like x direction. So in u direction, let's cut in u direction. So here's our section, and if you make it flat on the other plane, here's our section, and here is our A1, A2. For now, this line is not parallel to x nor y, so when I pinpoint my point, you have to use these 2 points anyway. It's A1, A2, and the slope of tangent line at that point is the rate of change in direction of u, right? When you move along the u direction, the slope, it tells you how much the z value changes, right? So if you have a larger u vector, then you have to take the length of the vector u to actually find the rate of change, because whenever you take the rate of change, it means that you're taking a unit vector rate of change in the x direction. In the y direction is depending on the unit rate of change in the x direction. By the way, so if u is unit vector, the norm is 1, then the slope of the section of the graph by the plane parallel to u is the rate of change of function at a in the direction of u. Now, let's take an algebraic way to find out the rate of change of u. So suppose that did I give coordinates u1, u2? Yeah. So let's take ct, which is a plus tu. So this is the straight line, parametrization of the straight line. So for example, it can be A1 plus TU1 and A2 plus TU2. Now, I want to see how it changes about the function. So I have to put the CT inside of F to see the change of value of F. So let's take CT. And this is my DT. Or my DT, okay? So I'm taking F as a real valued function. So DT is nothing but single value function, single variable function, right? And the point that I'm interested in is when t equals to 0, right? And also when t equals to 0, the velocity is u comma u2, which is u. So what I really want to see is d prime 0, which gives the rate of change of function f when t equals to 0, where the point in this curve CT moves along the direction of u, right? So I really want to compute the d prime 0, right? If I knew the formula of f, I could have just plugged in this formula into the function f as an x value and y value, and simply compute the derivative by the rule that I know for any single variable function. But suppose that I don't know the actual formula, but I know the derivative of function f, and I can use the chain rule. Then I can take the derivative of f at c0 times c prime 0. This is the chain rule that we mentioned before, right? Outside function times the inside function. And then let's think about what happens here. So this is f prime of c0, which is u, right? And what happens to c prime? This is just to the u. C0 is a, sorry. C0 is a, and c prime 0 is u. And so you see, always the derivative of multivariable function is a matrix. What's the size of this matrix? How many output variables we have in our examples? Two. Output is z. 1. So 1 by 2. 1 by 2 matrix. And how about this? This is two-dimensional vector. So always vector is column vector. So you multiply these two, you get 1 by 1 matrix, which is just a number here. But let's write in our definition. What's the derivative? How did you compute the derivative of multivariable function? You compute by partial derivative, right? So you only have one output. You can call it as a z, or you can call it as f. Let's call it as f. So first column element is fx, and you compute it at a. And second column element is by fy and a. And this is 1 by 2 matrix. And then you multiply it with u1, u2. So that's how you get fxa u plus fya u1 and u2. Same thing here, right? Using the partial derivative, you can find the rate of change in any direction at any point, knowing that you have a derivative of the function. Okay. question? Yes.
Is there any particular reason that we actually represent the f prime a vector as 1 by 2 matrix? Because I thought, actually the first time I thought it was 1 by 1 matrix because f prime a vector can be denoted by the addition, the sum of fx and fy.
Okay, so good question. So Hyungyu's question was why this derivative f prime is matrix of size 1 by 2, because he thought that the f prime is equals to fx plus fy, which is the real number, so it should be 1 by 1 matrix. Okay, so first of all, this has a meaning that it kind of measures how much the vectors in the tangent vector in the domain space changes in the target space. But in principle, this comes from the two variable function f, which takes 2 inputs and 1 output. Okay. So the derivative, let me state again. The derivative gives the information about how much the point moves in the domain affects the movement in the target space. So in this case, in our situation like z equals fxy, the change of value of function affects by 2 variables, x and y. So we need two independent directions to measure exactly how much the function changed. So if you simply combine these fx and fy as a summation or any others, then you cannot measure all direction of change, x and y. So you need to take x and y independently to measure exact amount of change in z direction. And also, think about the definition here, although you already know that this, but when you take a derivative, it must be m by n direction. So reason why we have m by n direction is that you take the n-dimensional vector as an input, and you get an output as m-dimensional vector by taking a multiplication with the derivative. So here it's the same thing here. We are taking a derivative of a multiplication with a derivative with a matrix. This u can change. If you have a different direction, the value should change. If you have 1 by 1 matrix, the result is just a scalar multiple of a vector, and you got the vector. But actually, we want to measure the difference of the number of d. It doesn't match, right? So you have to think carefully about the difference between the derivative and partial derivative. Okay? And there is actual importance of why we are taking about partial derivative here instead of taking any direction. Why we take the x and y direction? Why is it so important? Let me mention briefly about the gradient. So here's our definition. So let's generalize a little bit further from this example. Let's say f is a function from Rn to R. So it's a real valued function. And let's say I have f x1 to xn as an input. And the value is real number, okay? So if you think about the derivative, it's a 1 by n matrix. So basically fx1a fxn a. Okay, it's a 1 by n matrix. So the matrix itself doesn't give you any information about the actual change of the function. You have to provide a direction where the point move from A so that you can multiply that matrix, the column matrix in that case, to this 1 by n matrix to actually compute the total rate of change. However, you can consider this 1 by n matrix as if it's a vector again. This has one row, so usually we take the vector as a column matrix, but this matrix can take as a vector, n-dimensional vector. So we take a different symbol and different name for that kind of vectors called the gradient. And we take this notation called nabla. And nabla FA is called a gradient of f at A. And the coordinates are same as our coordinates in the derivative. Okay. So reason why I emphasize this and give you this definition is this is the crucial part that I'm going to explain the next time. So let me give one question and then finish our lecture today. Suppose you have a mountain like this. Okay. Maybe it has some creeks and it has some bumps. Suppose that you're here. You want to have a fastest trajectory that comes down to the mountain, down from the mountain. Okay? So you have to decide at each moment in which direction you have to move, right? So as if you're looking at the GPS map in two-dimensional. So let's say we have a mountain. This is a contour map of the mountain, like this. Suppose that you are here, and you have to decide in which direction gives you the fastest direction to the down to the mountain. So what's your guess? If you have this contour map in GPS, how would you decide which direction to move to get to the bottom of the mountain in the fastest way? Do you have any ideas? I'm sorry, redist?
Slow is sharp.
Oh, yes, the steepest direction, right? You have to move to the steepest direction. But if you're looking at the two-dimensional GPS map, which only gives you the contour map of the mountain, you don't know which one is the steepest. How would you find out the direction which is the steepest? Right, when you have contour lines are narrow each other, right? But suppose you don't have the contour for every height, right? It's impossible to draw the contour lines for every point, right? And also, even if you have a contour line for every point, you have to figure out which direction is has the narrowest contours in between. Like you have point contour lines like here. Okay, so you're right here. Would you like to go this way, which is where the contour lines are clustered together, or would you like to go this way? Second way. I draw it as a perpendicular line to the contour line where I'm at. Maybe you could move here, although this is not the steepest at this moment, but here you can go steepest line in faster way. But there's no strict answer. But you have, so in that moment, if you try to determine which direction is the steepest at that moment, then you have to choose this direction where you're moving moving toward the perpendicular direction to the contour line where you're standing at. This direction is the gradient direction. Okay, that's why I'm introducing gradient, because next time I want to talk about how would you approximate the regression line when the data are given. How would you find the best fitting curve of the data? So there's a formula, but I want to draw. I want to make a code, and also I want to give some small project about using the machine learning system. And we're going to use the gradient here. All right, so I talked too much, and it's time to stop. Thanks for listening. And before I finish, let me give a brief introduction about the assignment. So the weeks ago or 2 weeks ago, I added more tasks here. What I want to emphasize is that in project part, I put your first task questions. So let me elaborate the question more. So first question is set up a plan to solve your problem in several steps. So your problem could be large project. So break down into many steps as possible. And then what you actually have to do in this semester is something that you could do in 24 hours. Not 24 hours straight, but 24 hours in total, okay? So thinking about your spending entire efforts, your entire time and efforts in 24 hours and what you can do in those times. And then make your boundary of your project, okay? And then what you have to do is to write down specific tasks that you can do right now. Write down at least 3 specific tasks. For example, you have to be really specific. What I mean by really specific is, for example, I want to find out how to use Go language to solve your project. Then you have to first study about Go language, right? So your first task is open the golang.org and open the document page, and then there is a tour of Go page, and then the tour of Go consists of, say, 20 pages. your first task could be, I will read 1 to 10 pages of the tour of Go in the goerlang.org in next 1 hour or something like that. You have to be really specific so that you can mark that I finished my task. Okay? So the bad way of writing the task is I want to learn Go. That's too naive. That's too vague task. You have to be really specific. Okay? So write any 3 tasks that you can do right now to achieve your project. All right, that's my intention, and I think we have to finish here. If you have any question, please ask after class, and see you on next Tuesday.